All right, guys, so in the last section, we saw how to add inductors in series. The next natural logical step is to see how we can add inductors in parallel to define equivalent networks. And we're once again going to start taking a look at inductors and equivalent circuits. So the topic for now is inductors in parallel. And I want to start with two circuits, two networks. The first of the networks contains a total of 3 inductors, like this. The first inductor is characterized by an inductance L1, the second L2, the third L3. And on top of that, we have a second circuit that we're going to try to force to be equivalent that contains just a single inductor with inductance L equivalent like this. Now, if I happen to place a voltage V across these two terminals and I draw a current I, then if the two circuits indeed are going to be equivalent, then I must place the same voltage across these terminals and I should have the same current I flowing through those. Now, it should be clear if I take a look at the left-hand side circuit that there are two nodes. There's this top node. Similarly, there's this bottom node, like this. There are also some loops. We'll talk about the loops here in a second. But now that I have the nodes, I can define my circuit variables for the inductor. So I'm going to have V1 across L1 like this, V2 across L2 like that, and V3 across L3 like this. I can now define my currents to stay consistent with the passive sign convention. So I'm going to have I1 flowing through L1 there, I2 flowing through L2 there, and I3 flowing through L3 right there. Now, hopefully, one of the things that you can see is there are quite a number of loops here. And I'm not going to do this explicitly. Hopefully, you've seen enough circuit analysis to be able to recognize this. Notice that there are quite a number of loops like this. And if I use KVL around those loops, one of the things that you should be able to hopefully see now by inspection is that the voltage V1, V2, and V3 are identical, and they're identical to V. So here, by KVL around the blue loops, in other words, I add up those voltages, a conclusion that you should be able to reach is that V1 is the same as V2, is the same thing as V3, is the same thing as V. Now this is important because this is the defining property for elements to be in parallel. So this defines here inductors in parallel. Right. Now, one thing that I also want to do is, before I do anything else, I do want to remind you of the IV characteristics of inductors. So recall for inductors, remember that the voltage was equal to the inductance times the time derivative of the current. Right? Now this is the IV characteristic in differential form. This can actually be inverted to be rewritten in differential form, right? So the current as a function of time in an inductor is 1 over the inductance. The time integral from t naught to our variable t. Notice that the variable t is actually one of the bounds of the integral. The voltage as a function of the dummy variable tau, which is going to be integrated across. And we also need to take into account that there is a current, a non-trivial current that may exist at time t equals t naught. So this is the current at time t equals t naught. So there's a constant there, right? Now, this is the general IV characteristic for an inductor. So if you happen to know the voltage as well as an initial condition, you can write down what the current is. And I'm actually going to use this a total of 4 times, right? So using the IV characteristic 4 times, I can definitely say that the current I1, which in general is a function of time, is equal to 1 over L1, the time integral from t0 to t, the voltage V1 integrated with respect to tau, a dummy variable, plus whatever current existed in that inductor at t0. I can write down the same thing for I2, except every time you see a 1, you now replace it with a 2. So this is the IV characteristic for the second inductor, and you guessed it, for the third one, it takes on the exact same mathematical form as the previous two, like this, right? And notice that we can also apply this to the circuit on the right, the equivalent circuit. So here on the second circuit, we have that the current as a function of time is equal to 1 over the equivalent inductance, the integral from t0 to t, the voltage integrated with respect to the dummy variable tau, plus the current that existed at time t0. So notice that this is essentially a set of 4 formulas. The first 3 apply to the network, while the last one applies to the equivalent inductor. Now this is as far as we'd be able to go if we had only used KVL on the circuit on the left. But we also have KCL to exploit. Now, you can apply KCL either to the top node or the bottom node. It really doesn't matter. It's going to lead to the same thing. So if I actually apply KCL to the top node, the sum of the currents flowing in has to equal the sum of the currents flowing out. Well, one of the things that we can definitely say is that the total current I, it must be equal to I1 plus I2 plus I3, right? So here I can actually have those 3 expressions added together. But one thing that I'm going to do right off the bat, because it's going to simplify things, I don't want to write out this huge equation. Remember the defining property. V1, V2, and V3 should all equal the same external voltage V. That means that this voltage, and that voltage are all the same voltage. So using the top equations in KCL, I get that I as a function of t is equal to 1 over L1, integral from t0 to t of V integrated with respect to tau. Whoops, not t. It should be tau plus I1 of t0 plus 1 over L2, the integral from t0 to t of V of tau d tau plus I2 at t0, and then lastly 1 over L3, the integral from t0 to t of V of t, or V of tau d tau plus I3 of t0. Now notice that this, even though they're integrals, they're in common to each one of the terms. So I can actually group the first of each one of the integral terms together, and then I'm actually going to group these constants together. So here I have that I of t is equal to, well, 1 over L1 plus 1 over L2 plus 1 over L3. The integral from t0 to t, V of tau d tau plus I1 of t0 plus I2 of t0 plus I3 of t0 like this. And this is, once again, where the magic happens, right? If the left-hand side circuit is going to be equivalent to the other side, then those voltages and currents must be identical. So here, this current and this nasty current over here, they must be the same. So we can equate them. In which case, I have 1 over L1 plus 1 over L2 plus 1 over L3. The integral from T naught to T, the common voltage integrated with respect to tau, plus the constant I1 of T naught, I2 of T naught, I3 of T naught. Well, that has to equal 1 over L equivalent, the same integral from T naught to T, V of T naught d tau, plus I of T naught. And notice that we have now two equivalences that must be true. Notice that this right here is in common to that, which means that for these two to be the same, these two must be true. And similarly, these constants must be equal to one another. So we have actually two new conclusions. Two conclusions. The first is that 1 over L equivalent is equal to 1 over L1 plus 1 over L2 plus 1 over L3. And that in the equivalent circuit, the initial current at T naught must be, by KCL, the sum of the currents that exist in each one of the inductors. Now again, these two circuits will be equivalent. If they happen to be in parallel, I can replace the entire network of inductors with one single equivalent inductor, provided the reciprocal of the equivalent inductance is the sum of the reciprocals of each one of the inductors in the network. Very similar to resistors in parallel. And I can guarantee this will help in simplifying your networks even before you begin analyzing them.